Today everyone, our next topic is all about couplings, but before that, let me show to you our table of contents. First, what is couplings? Second, what are the types of couplings? And lastly, the mathematical approach. Let's know first, what are couplings? A coupling is a term as a device used to make permanent or semi-permanent connection, whereas a clutch permits rapid connection or disconnection at the will of the operator. A coupling may also be defined as a mechanical device that connects the ends of nearby pieces or objects. Couplings do not generally enable shaft separation during operation. However, torque-limiting couplings can slide or detach when a certain torque limit is exceeded. Coupling selection, installation, and maintenance can result in decreased maintenance time and expense. And there are two types of couplings. The first one is the rigid coupling, and the second one is the flexible coupling. And now, let's talk about the first type of couplings. The first one is rigid coupling. It is used to connect two shafts which are perfectly aligned. Also, it is the one that does not allow axial or radial motion between the driving and driven shafts. Rigid couplings are either integrated with the forging of the shaft or shrunk onto the shaft. Monoblock half couplings on turbine rotors are currently standard practice. Shrunk-on couplings were utilized on turbines and are still used on generators. There are three types of rigid coupling, and they are important from the subject of point of view. First, sleeve or muff coupling. Second, clamp or split muff or compression coupling. And lastly, flange coupling. And now, let's talk about the first type of rigid coupling, the sleeve or muff coupling. It is a basic type of coupling. This consists of a pipe whose bore is finished to the required tolerance based on the shaft size. Based on the usage of the coupling, a keyway is made in the bore in order to transmit the torque by means of the key. Sleeve couplings are nothing more than a thick hollow cylinder pipe. The sleeve is made with the shaft's diameter in mind so that the shaft fits precisely into the sleeve. Both the driver and the driven shafts are then placed into either side of the sleeve. In addition, two or more threaded holes are placed into the sleeve as well as both shaft ends to prevent them from moving in the longitudinal direction when the bolts are inserted into them. The keyway and the key also prevent the shaft and sleeve from slipping. The second one is the clamp or split muff or the compression coupling. It is a rigid type of coupling. In this coupling, the sleeve is made of two halves. The halves of the muff are made of cast iron. One half of the muff is fixed from below and the other half is placed from above. The muff have a semi-cylindrical form that fits over the shaft. Threaded holes are supplied on the muff to allow steel bolts or studs to be used to connect the shaft. This connection is unique because it may be installed and dismantled without affecting the position of the shaft. The last type of the rigid coupling is the flange coupling. Flange coupling involves bringing the two tube ends together in a flush-sealed manner. The two-piece coupling unit consists of a key the receiving side for the flange end to be fastened. The reason being it may be married to the opposing tube end, which also has a flange end. Flange coupling is similar to sleeve coupling because it is simple to construct. Flanges are present on both sides of the two sleeves. In this case, both flanges are made up of an equal number of threaded holes for fastening. Bolts and nuts are then used to connect the flanges. On the hub and shafts, a key area is also supplied to prevent slippage. Applications of couplings. First, sleeve coupling are used where the shafts don't require any alignments and load capacity is light to medium duty. Next, split muff coupling are used for medium to heavy duty load with moderate speed. Last, flange coupling are used for medium and heavy duty industrial applications. Did you know that couplings connect two shafts together? Quite simply, the main aim of couplings is to connect two shafts together so torque can transmit from one shaft to the other. When one shaft spins, the coupling connects the two, enabling the second shaft to spin also. Couplings help to transmit power. This is their primary function and their basic principle of operation. Let's have an example of a problem solving for a flange coupling. Two shafts of diameter 30 mm each are connected by a flange coupling. 6 bolts, each of diameter 8 mm, are used on a pitch circle of diameter 90 mm. If the allowable shear stress of the bolt material is 80 MPa, what is the torque transmitting capacity of the bolts to the nearest 10 units? First, we need to find the given. Pitch circle diameter of flange is equal to 90 mm. Diameter of bolts is equal to 8 mm. Allowable shear stress of a bolt is equal to 80 MPa. The required for this question is torque transmitting capacity of the bolts. Now, let's have the solution. And the final answer for this question is 1085.7 Newton meter.
Flexible coupling are used to connect two shafts with both lateral and angular misplacement. Flexible coupling has a characteristic to accommodate misalignments as follows: 1.5 degree for angular and 5 mm for axial.
As we discussed, that a flexible coupling is used to join the abutting ends of shaft when they are not in the exact alignment. In the case of direct coupled drive from a prime mover to an electric generator, we should have 4 bearings and a comparatively close distance. In such a case, and many others, as in direct electric drive from an electric motor to a machine tool, flexible coupling is used so as to permit an axial misalignment of the shaft without undue absorption of the power which the shaft is transmitting.
The 3 main types of couplings in flexible are the following. First, the pin bush coupling. Second, the Oldham coupling. Third, the universal coupling.
Moreover, flexible couplings, which make up 90% of coupling solid, are designed to transmit torque from one shaft to another when the two shafts are slightly misaligned while permitting radial and axial displacement and rotation. To be considered flexible, a coupling must handle parallel and angular misalignment. These couplings also anticipate the transmission of fluctuation of torque and speed from one rotor to another by flexing itself and are thus help in providing nearly smooth transmission of speed and torque. We can obtain a wide range of torque capacity depending on the type of flexible. These types of couplings are used in applications that call for curved or deflected layouts, or when systems are exposed to the outside forces beyond normal static conditions, such as seismic wave or vibration or even a noise attenuation. Flexible couplings can be used in servos with low or moderate torque. It can be potential to shaft misalignment such as machining tool, semiconductor manufacturing, and packaging equipment. The advantages are as follows. They compensate for misalignments, movement, or deflection. They are very useful when having quick and short starts. They are highly capable of reducing transmission of shocks, loads, or vibration. The disadvantages are they normally provide less torque transfer, they have a high cost due to additional parts, they don't reduce backlash to at zero level, and they have more complicated operations and maintenance.
The bush coupling is an alteration for flange coupling. It consists of rubber, nuts, and pins to connect two shafts with an alteration of misalignments. Bush pin couplings composes of driving shaft, driven shaft, flanges, rubber brush, brass brush, bolts, and nuts.
The function of a flexible coupling pin bush type is to connect two shafts having both lateral and angular misalignment. Its construction has a modification of rigid flange coupling. It consists of two flanges mounted on the shaft with the help of keys. The flanges are connected together by means of pins and nuts. Pins is covered by bush, having flexible materials such as rubber and leather. In terms of working, power is transmitted from driving shaft to flange through key. Then it is further transmitted from driving flange to driven flange through a pin and nut. Again, power is transmitted from driving flange to driving shaft through key. Moreover, it has an advantage to be torsionally more stiff, no lubrication, and less maintenance. It has a good vibration damping and shock absorbing qualities. And lastly, it had a more misalignment allowable than the rigid couplings. Its limitations are sensitive to chemicals and high temperature, usually not torsionally stiff enough for positive displacement, larger in outside diameter than metallic coupling, and difficult to balance. A bush pin flexible coupling has been shown and is a modification of a rigid type of flange coupling. The coupling bolts are known as pins. The rubber or leather brushes are used over the pins. The two hubs of the coupling are dissimilar in construction. A clearance of 5 mm is left between the base of the two hubs of the couplings. There is no rigid connection between them and the drive to take place through the medium of the corresponding rubber or leather brushes. In designing the bush pin flexible coupling, the proportions of the rigid type flange coupling are modified. The main modification is to reduce the bearing pressure on the rubber or leather brushes, and it should not exceed 0.5 Newton per millimeter squared. In order to keep the low bearing pressure, the pitch circle diameter and the pin size is increased. Let L is the length of the bush in the flange, D is the diameter of the bush, P sub B is the bearing pressure on the bush or pin, N is the number of pins, and D1 is the diameter of pitch circle of the pins. In solving, we start to bearing load acting on each pin. W is equal to P sub B times D sub 2 times L. The total bearing would be W times N is equal to P sub B times D sub 2 times L times N. In terms of torque, we have the formula of T is equal to W times N, the quantity of T sub 1 over 2, or P sub B times D sub 2 times L times N, the quantity of D sub 1 over 2. The threaded portion of the pin in the right hand flange should be a tapping pit in the cup hub to avoid bending stress. The threaded length of the pin should be small as possible so that the direct shear the stress can be taken by under threaded neck. We have the formula for the direct shearing stress as direct shearing stress is equal to W over phi over 4 times D raised to 2. Since the pin, the rubber on the leather bush is not rigidly held in the left hand flange, therefore the tangential load W at the enlarged portion will exert a bending action on the pin. The bush portion of the pin acts as cantilever beam of the length L. Assuming a uniform distribution of the load W along the bush, the maximum bending moment of the pin would be M is equal to W times L sub over 2 plus 5 mm. And now our bending stress is equal to M over Z, or is equal to W times L over 2 plus 5 mm over pi over 32 times D raised to 3. Since the pin is subjected to bending and shear stress, therefore the design must be checked either for the maximum principal stress or maximum shear stress. If it's a maximum principal stress, it would be equal to 1/2 over stress plus square root of stress squared plus 4 tau squared. And for maximum shear stress, it would be 1/2 times square root of stress squared plus 4 tau squared. Sample problem. Design a bushed pin type of flexible coupling to connect a pump shaft to a motor shaft transmitting 32 kW at 963 RPM. The overall torque is 20% more than mean torque. The material properties are as follows. A. The allowable shear and crushing stress for shaft and key material is 40 MPa and 80 MPa respectively. B. The allowable shear stress for cast iron is 15 MPa. C. The allowable bearing pressure for rubber bush is 0.8 Newton per millimeter squared. D. The material of the pin is same as that of the shaft and key. As we lay down are given, we will proceed to number 1. Design for pins and rubber bush. First of all, let us find the diameter of the shaft. We know that the mean torque transmitted by the shaft is T mean is equal to power times 60 over 2 pi n equals 32 times 10 raised to 3 times 60 over 2 pi times 960 RPM, equivalent to 318.3 Newton meter. And the maximum of overall torque transmitted would be T max is equal to 1.2 times T min. So is equal to 1.2 times 318.3, equivalent to 382 Newton meter, or 382 times 10 raised to 3 Newton millimeter. We also know that the maximum torque transmitted by the shaft, T max, would be getting the diameter to D cube is equal to 382 times 10 raised to 3 over 7.86, equivalent 48.6 times 10 raised to 3, or in diameter of 36.5 millimeter. We have discussed the rigid type of flange coupling that the number of bolts for 40 mm diameter shaft are 3. So, in the flexible coupling, we shall use the number of pins number as 6. Diameter of pins D1 or D sub 1 is equal to 0.5 D times square root of N is equivalent to 0.5 times 40 over square root of 6, coming up for 8.2 mm. Number 2. Design for hub. We know that the outer diameter of the hub is D is equal to 80 mm and L or the length is 60 mm. Let us now check the induced shear stress for the hub material, which is the cast iron. Considering the hub as a hollow shaft, we know that the maximum torque transmitted would be 382 times 10 raised to 3 is equal to pi over 16 times tau C times the quantity of D raised to 4 minus D raised to 4 over D. Take note that the uppercase D is outer diameter and the lowercase would be the inner diameter. Then proceeding to equivalent of pi over 16 times tau C, quantity of 80 raised to 4 minus 40 raised to 4 over 80. And it would be equal to tau C 94.26 times 10 raised to 3. Equating to the formula, we can get 4.05 MPa or 4.05 Newton per millimeter squared, given the fact that we have the 382 times 10 raised to 3 earlier. Since the induced shear stress for the hub material is less than the permissible value of 15 MPa, therefore the design of hub is safe. Number 3. Design for key. Since the crushing stress for the key material is twice its shear stress, therefore a square key may be used from the table. We will find that the shaft of 40 mm diameter, width of key is equivalent to W 14 mm, the thickness would be T is equal to 40 mm as well. The length of key L is taken equal to the length of hub. length is equal to 1.5 times d or the diameter. 1.5 times 40 would be equal to 60 mm. Let us now check the induced stresses in the key by considering it in a shearing and crushing. First, considering by shearing, we know that the maximum torque transmitted would become as follows. Deriving the equation, we will now have 382 times 10 raised to 3 is equivalent to L times W times tau K times D over 2 equals 60 times 14 times tau K times 40 over 2 is equivalent to 16,800 tau K. Then tau K would be 382 times 10 raised to 3 over 16,800, gaining a considering shearing stress of 22.74 MPa. Next, considering by crushing, we know that the maximum torque transmitted will become 382 times 10 raised to 3 equivalent to L times T over 2 times tau CK times D over 2, equating 60 times 14 over 2 times tau CK times 40 over 2 is equivalent to 8,400 tau CK, equating again tau CK is equal to 382 times 10 raised to 3 over 8,400, gaining a 45.48 MPa for crushing. Number 4. Design for flange. The thickness of flange is taken as 0.5 diameter. Therefore, thickness of flange is equal to 0.5 diameter, equating 0.5 times 40 equivalent to 20 mm. Let us now check the induced shear stress again in the flange by considering the flange at the junction of the hub and shear. We know that the maximum torque transmitted Tmax would be equal to 382 times 10 raised to 3 equivalent to pi d squared over 2. Take note that it is a outside diameter times tau c plus thickness of flange equating to pi times 80 raised to 2 over 2 times tau c times 20, gaining 201 times 10 raised to 3 tau c, equating again tau c would be equal to 382 times 10 raised to 3 over 201 times 10 raised to 3, gaining a 1.9 MPa. Since the induced shear stress in the flange of cast iron is less than 15 MPa, therefore, our design of flange is safe.
Oldham couplings are a 3-coupled couplings. It has a 2 hubs and 1/3 disc. It connects 2 shafts with 2 different axes. The Oldham coupling composes of driving shaft, driving flange, driven shaft, driven flange, central flange, slot, thumb, and frame.
Proceeding, the main function of Oldham coupling is for connecting shafts by parallel shafts whose axes are at small distance apart. It means that it has an offset direction or distance to transmit a powerful motion or power. Its construction has the following types. 2 flanges are placed at the end of 2 shafts which are to be connected. These flanges are rigidly fastened and the end of the purging. Both flanges should have 1 slot. The slot of both flanges are perpendicular to each other. Between these 2 flanges, a central flange is inserted to fit into slots for both flanges. Central flange has also 2 tongues for connections. The Oldham coupling works when driving shaft rotates along with the flange forged to it. It also rotates the central flange placed in slot to drive the other flange on the other side. Then the power is transmitted to the driven shaft by a central flange. Additionally, Oldham coupling is used to join 2 shafts which have lateral misalignment. It consists of 2 flanges A and B with slots and central floating part E with 2 tongues T1 and T2 at the right angle as shown in the figure below. The central floating part is held by means of a pin passing through the flanges and the floating part. The tongue TI fits into the slot of flange A and allows for to and fro relative motion of the shafts, while the tongue 2 fits into the slot of the flange B and allows for vertical relative motion of the parts. The resultant of these two components of motion will accommodate lateral misalignment of the shaft as they rotate. A universal or Hooke's coupling is used to connect two shafts whose axes intersect at a small angle. The inclination of the two shafts may be constant, but in actual practice, it varies when the motion is transmitted from one shaft to another. The main application of the universal or Hooke's coupling is found in the transmission from the gearbox to the differential or back axle of the automobiles. In such case, we use two Hooke's coupling, one at each end of the propeller shaft, connecting the gearbox at one end and the differential on the other hand. A Hooke's coupling is also used for transmission of power to different spindles of multiple drilling machine. It is used a key joint in milling machines. Moreover, in designing an universal coupling, the shaft diameter and the pin diameter is obtained as follows. Let D is equal to the diameter of the shaft. D sub P is the diameter of the pin, and tau 1 are the allowable shear stress for the material of the shaft and pin respectively.
Universal coupling is known as cardan joints or Hooke's joints. This also connects two shafts with different axes of inclination with each other to transmit power and work. The universal coupling composes of driving shaft, driven shaft, fork ends, and cross.
Mathematically speaking, the torque transmitted by the shaft would become torque is equal to pi over 16 times tau times diameter cube. From this relation, the diameter of shafts may be determined. Since the pin is in double shear, therefore the torque transmitted would become T is equal to 2 times pi over 4 times diameter of pin squared times tau sub 1 times D. We also take note that when a single Hooke's coupling is used, the ratio of the driving and the driven shaft speeds is given by N over N sub 1 equal to 1 cosine squared angle plus sine squared alpha over cosine alpha, or given by simplified form of N sub 1 is equal to N times cosine alpha over 1 minus cosine squared theta times sine squared alpha, where the N is the speed of the driving shaft in RPM, the N sub 1 is the speed of driven shaft in RPM, alpha is the angle of inclination of the shafts, and theta would become the angle of the driving shaft from the position where the pins of the driving shaft fork are in the plane of the two shafts. Also, we know that the maximum speed of the driven shaft would become N sub 1 max is equal to N over cosine alpha, and its minimum would become N sub 1 minimum is equivalent to N cosine alpha. From the above, we see that for a single Hooke's coupling, the speed of the driven shaft is not constant but varies from maximum to minimum. In order to have a constant velocity ratio of the driving and the driven shafts, an intermediate shaft with the Hooke's coupling at each end is used. Sample problem. An universal coupling is used to connect two mild steel shafts, transmitting a torque of 5,000 Nm. Assuming that the shafts are subjected to torsion only, find the diameter of the shafts and pins. The allowable shear stresses for the shaft and pin may be taken as 60 MPa and 28 MPa respectively. Solutions. We have a given T is equal to 5,000 Newton meter or equivalent to 5 times 10 raised to 6 Newton millimeter. Tau, 60 MPa, equivalent to 60 Newton per millimeter squared. Tau sub 1, 28 MPa, or equivalent to 28 Newton per millimeter squared. First, we will take a look on the diameter of the shafts. So let D is equal to diameter of the shafts. We know that the torque transmitted T would become 5 times 10 raised to 6 is equivalent to pi over 16 times tau times D cube, equating pi over 16 times 60 times D cube is equivalent to 1.8 diameter cube. Then, we should substitute and re-equate the diameter to D is equal to cube root of 5 times 10 raised to 6 over 11.8, gaining a diameter of 75 millimeter. Next, for the diameter of the pins, we have D sub P, or the diameter itself. We know that the torque transmitted would become 5 times 10 raised to 6 is equivalent to 2 times pi over 4 times D sub P squared times tau sub 1 times D, equating again to 2 times 2 times pi over 4 D times P squared plus 28 times 75, equating to 3,300 D sub P squared. Simplifying, diameter of pins is equivalent to square root of 5 times 10 raised to 6 over 3,300, gaining a 39 millimeter diameter or rounding off to 40 millimeter.